Imagine you're at a big concert, looking away from the stage and towards the crowd. Do you think you could tell when the big hits come on just by watching the audience? Of course you could. People would move more, dance more, jump more. Not every individual, perhaps. But by looking at the crowd as a whole, you could tell overall when the excitement was building. Well, this is not very different from what happens at the atomic scale when things heat up. This is real chem. Temperature is related to the motion of molecules in a sample, but there are a lot of molecules in a sample and they aren't all doing the same thing, just like in a crowd of people at a concert. If we are going to make sense of crowds of people or molecules, we need some tools to deal with averages and distributions. Let's explore. We experience temperature on a daily basis. Touch a hot object like a stovetop, and you feel the heat being transferred to your hand. At the atomic scale, the atoms in the stovetop are moving faster than those in your hand. When your hand comes in contact with the stovetop, please don't try this at home, the atoms in the stovetop collide with those in your hand and transfer some of their kinetic energy. This raises the temperature of your hand, often to an unpleasant extent. So temperature is all about kinetic energy. In fact, one definition of temperature is that the temperature in Kelvin is proportional to the average kinetic energy of the particles in a sample. Double the temperature of your stovetop, and the average kinetic energy of the atoms in your stovetop doubles. It's easier to visualize motion for gases, so let's switch to two samples of nitrogen gas, one at 100 Kelvin, the other at 200 Kelvin. The molecules in the hotter sample are clearly moving faster, but it's hard to see what is going on because there are a lot of particles and they're all moving at different speeds. This is where graphs of distribution functions come in handy. We pick some range of kinetic energies on the x-axis, and the area under this curve, called the distribution function, is the number of particles moving with kinetic energies in that range. This gives us a more detailed view of how the sample at 200 Kelvin compares to that at 100 Kelvin. When we double the temperature, we lower the number of molecules moving with low kinetic energy and increase the number of particles moving with high kinetic energy. This distribution is called the Maxwell-Boltzmann distribution. When we show it with kinetic energy on the x-axis, its shape depends only on the temperature. For example, if I compare a sample of nitrogen gas to a sample of helium gas, both at 200 Kelvin, the distribution of kinetic energies are identical. A helium atom is a lot lighter than a nitrogen molecule, but the mass of the particle doesn't matter. Or, mass doesn't matter for kinetic energy, but the relation between kinetic energy and speed does involve the mass of the particle. Kinetic energy is 1/2 mv squared. So when we switch the x-axis from kinetic energy to speed, we do see a large difference. Helium is less massive than nitrogen, so it must move a lot faster to have the same kinetic energy as nitrogen. It's amazing that this universal nature of the Maxwell-Boltzmann distribution doesn't only apply to motion in gases, it applies to liquids and solids. So, just like in that crowd at the concert, it's the collective overall change in energy that matters, not the movement of one molecule. And when the collective starts to move, you definitely know it's happening, whether it's people or particles who are doing the dancing. So explore, and remember to have fun.